Alright, today I'm going to be deriving kind of the formula for potential energy. So, if you lift a mass up a height like h, right, what's going to be the work done by you, right? Well, the answer is mgh, right? But that's not really that trivial, because if you think about it, the force is not going to be constant throughout your whole lift, because if it is, then you're not going to be able to lift it, because the force you're applying on the box is going to be equal to its weight. So nothing's going to happen. So you're going to have to apply a larger force at first, at least. So how do we kind of figure this out? Well, all we have to do is say that the work done will be just the integral of the kind of net force acting, or I guess I'll say the net work done on the box is going to be F net of, let's say, x. So I'm going to call this my kind of x-axis, like that. So I'm going to say this is my x, times dx. Now what I can do is I can use Newton's second law to rewrite this as the integral of m times, I'm going to write this as v dot, and then I'm going to replace the dx with dx dt, dx by dt times dt, right? So I'm just going to, do that. And what that allows me to do is that allows me to just rewrite this as m times the integral of v dot times v dt. And now I can use the chain rule, basically. Or really, I'm going to rewrite this as just v times dv dt times dt. And you can clearly see that like the dt's are going to kind of cancel. And I'm going to end up with m times the integral of v dv. And from this, I'll just get basically 1/2 mv squared, right? And this is going to be, I guess from v naught, from your initial velocity to your final velocity. So that's going to be basically the difference in the kinetic energy of the box. But we want the box to be stationary at the beginning and at the end of the ascent, basically. So we want this to be 0, because we want Vf to be equal to V naught. So that's going to make the whole thing 0. So basically we want the net work done to be 0. And now what I'm going to do is I'm going to rewrite the force. I'm going to kind of split it up into two parts, into its kind of constituent forces. So I'm going to write it as my force, right? So I'm going to write F me of x dx, and I'm going to split up the integrals immediately, minus the integral of mg dx. So basically what I've done is I've split up this net force into F me minus mg, right? So my force subtracted by the force of gravity, because it's in the other direction. And I'm going to be integrating this from 0 to h, right? Because I'm lifting it from point 0 to h. And so this is going to just be, and I'm going to also rewrite this as the work I do, because this is kind of what we're looking for, right? So the work I do is going to be this. So it's going to be F me minus the integral of mg from 0 to h over dx. So that's just going to evaluate to, I should write this like that. Okay, so F me minus mgh, and this is again going to be 0, because again we want the net work to be 0. And if we just rearrange this, we'll just end up with W me is equal to mgh. And yeah, there's the formula for the work I do. So it's pretty nice. And yeah, so that's kind of a way you can prove that the work you do when lifting a box is just mgh, no matter what kind of force you apply on it, like throughout the whole ascent, it doesn't matter. You'll end up with the same amount of work done. So I think that's pretty neat.